Chapter 3, Math Functions, Binary, Strings, and Objects. Wish me luck. This is going to be an interesting one. So, a lot of little things to cover here. Nothing particularly hard, just a lot of little things. Python functions, right off the bat, we're going to look at some math functions from the math module. We've seen several functions already. We've seen the print function, the int function, the eval function. What is a function? It's a group of statements that perform a particular task. And we can broadly classify functions into those functions that we are going to define, we're going to make ourselves. We're going to come up to that way later in this discussion. And then also functions that are already made for us, that are pre-built and that are available for us from the various libraries and the parts of the language. And we've been using functions from day one, as mentioned, eval, input, print, and other functions. These are part of the Python library. What we want to see now, what we want to see now are some built-in math functions. So we have here absolute value, max, min, pow, round, and we've even seen some of these. So I want to come over here, for example, let's look at the Python function for min. I can print the min of 2 and 8. That's going to print for me the minimum value of those two values. It prints a 2. If I had made this 13, it'll print for me 8. That's the minimum value of 13 and 8. I could have saved that into a variable instead of printing. I could have said the minimum value equals 13, 8, and then I could just print that variable, the minimum value. So this is an example, and I'll run this one. We get 8. Let's put in two other values just so we're good here. How about we put 2 and 9? The smallest value, of course, is 2. If I make this max, that'll give me the maximum value of 2 and 9, which is 9. That's just one example. We've seen the pow, for example. If I want to print pow of 2, 3, what does that do? That will print 8. It'll print the result of raising 2 to the third power. It's just an exponent function for us. We have a round function. We have ABS, which gives us the absolute value, ABS. And here I want to put in some number, the ABS of -4. We should expect that that's going to give us 4, right? Absolute value. These are easy functions that we've seen probably in what? 3rd grade, 4th grade, the minimum of 2 numbers, the maximum of 2 numbers, the absolute value of a given number. Pretty straightforward. And here are several examples on this particular slide. So there's also additional math functions that Python gives to us that can be found inside the math module. These include many famous constants, such as pi, and many other famous math functions. We're talking about trigonometry functions, sine, cosine, tangent, log. Now we're talking about pre-algebra. These are things that might be scaring people, making us a bit concerned. Are we going to be getting into high-level math? No, we're not. But we're going to show you how we can use these libraries if you wanted to. If you were given a particular problem that needed math, which we won't really give, but if you had one that needed to use trigonometric functions, it's important to know that Python gives you libraries, gives you a module that gives you access to these functionalities to help you solve your problem. So step 1, as I just showed at the bottom of the slide, is we need to start by importing math. So in our program, I'm going to come to chapter 3 notes. I need to type import math. And this is only necessary to use the additional math functions. The basic ones that I just showed you, just to print the max of 3 and 4, to print 4, we don't need to import math. This max function is already understood by the interpreter. But other functions, if I wanted to print the sine of some number, the sine of what? The sine of 180 degrees. Well, when I run this, Python's like, I'm confused. What is sine? And the reason for that is we have to import the math module, in order for those additional functions to be available for us. Let me go ahead and clear this out. So we can import the math module, and here's many example functions. I mentioned the trigonometric functions. We have some functions that we've seen in pre-algebra and algebra. Also in pre-calculus, we have now log. Square root, that's nothing too complicated. I hope we know how to do square root. So let me do this one. If I were to type in print SQRT of 100, we may think I go and I run this and I'm going to have absolutely no problem, but notice it still says square root is not defined. Why is that? Because we have to actually type in math dot square root. We're importing math, and then I need to actually type math dot square root to use that particular function. What's another one in here that we might be familiar with? Sine again. We could take the sine. I'm trying to think about the, so this is the, so I'm thinking of the sine graph. So the sine of pi, for example. So how about if I said math dot sine of pi? That should be 0, right? And 2 pi is 0. How about we do pi over 2? So can I say math dot pi divided by 2? Is that going to give me 1? It's been a while. No. Math has no attribute pi. How do I get to pi? Now I'm curious. Well, let's just make it 3.14159. 3.14159. 3.14159. And is this going to give us close to 1? Yeah, that's basically close to 1. So you know what? Math.pi, I'm curious. I'm going to pause very quickly. I'm curious how we get that. Boo! I had it capitalized. Math.pi. I don't like that at all, and we'll talk about why later. So here we get 1.0. So these are just functions that are available to us. If you're not a math person, you don't want to have to use these functions, and you're never presented with such problems, fantastic. You don't need to use them. However, there are two that are shown here that are super valuable, super helpful, super important, and that is ceil and floor. So I want to cover what do the ceil and floor functions do. I'm going to pull over and come over to this trusty tablet here. What does the ceil function do? When you send to the ceil function a number, let's say we send over 4.8. What does the ceil function do? It basically says, give me the ceiling of that number, which is 5. Now, what do we mean the ceiling of that number? So what I tell students to do is I say, imagine we have a vertical number line. So here's a number line. It's a vertical number line. And here we have, let's say this is, I'll put 0 here. This is 0, this is -1, this is -2, this is 1, 2, 3, 4, running out of space, 5. So 4.8, where's 4.8? It's about right here on that vertical number line, right? So what I want you to do is identify where 4.8 is and now look up. What is the whole number above 4.8? The answer is 5. So that's what ceiling does. What is the ceiling of 4.000001? Well, where's 4.01 on this number line? It's like right here. It's above 4. So look up. What is the whole number above 4.01 or 4.00001 on the vertical number line? The answer is 5 again. So that's what ceiling does. It basically takes your number and it picks the whole number above that number. And floor does the opposite. Floor, if I were to erase this, erase ceil, and now let's put floor here. What does floor do? Floor gives you the whole number below. So the floor of 4.8 is 4. The floor of 4.00001 is 4. Also the floor of 4.999999, right? Even the floor of that number is, in fact, the number 4. So that is floor and ceiling, and you're going to see there are many problems that floor and ceiling are super, super helpful with. Many problems are going to be coming to, and some they're going to be in some of the problems they're going to solve online. So these are just some of the example functions, and here are some sample outputs from those functions. So I give one example here in the slide where I say, and I warn people, I say, don't be concerned, don't start wanting to give up and think, oh, this is math, it's formulas, I'm too scared, and it's going to be a problem. Especially, let's come to the next page and say, hey, what if you want to compute those 3 angles? Well, you'd have to know all of this math, which is like, oh no, I can't do that, which is fair. We're not covering the math. I'm not going to have those type of problems. That's beyond the scope of what we're covering here. The purpose is to simply illustrate that if you had a program that you needed to perform these type of computations and calculations, the purpose is to demonstrate that Python gives you the ability to compute those things within the math library. They give you the access to arctangent. They give you access to these other functionalities. So we don't need to fully understand this math. That's beyond the scope. Just want you to know that that is there for you if you need it. All right, next thing. Strings and character. What is a string? We've covered this. A string is a sequence of 0 or more characters. And this string could be a string of just numbers, 3.145. That's a string. And how many characters are in this string? 1, 2, the decimal is a character, 3, 4, 5. That has 5 characters in it. As we know, a string in Python has to be enclosed in either a pair of double quotation marks or a pair of single quotation marks. And here's many strings. The message, good morning, letter A again, but now with single quotation marks. And here's a number string. So Python does not have a particular data type for a single character, when many other languages do. Many languages, they distinguish between a single character versus a string with 0 or more characters. Python only has strings. A single character is simply represented in Python as a single character string enclosed in either double quotes or a pair of single quotes, either one. But for the purposes of being consistent with other languages, I like to give a reminder that when I cover Python, I normally follow the paradigm of other languages where a single character, we enclose it within single quotation marks, and a string of many characters we enclose within a pair of double quotation marks. Now we take a brief hiatus. What is this brief hiatus going to be for? To do several things. We want to discuss what computers actually understand. They understand zeros and ones. And we want to cover character encoding and why this is so important. We want to have an introduction on bits, on bytes, and some people are like, oh no, what are bits and bytes? It sounds scary. We want to talk about binary numbers, hexadecimal numbers, decimal numbers, and how to convert between them, but it's not going to be bad. Some of you are like, oh no, this is not what I signed up for. It's not going to be bad at all. And it's really important to have this, to lay down this strong foundation of understanding what are binary numbers, why are they important, and how are they useful to us. And then as well as what are hexadecimal numbers and their importance. So a very quick primer on numbers. What is the most common number system that we use day in and day out? It is the decimal, it is the base 10, the decimal number system. And what does that mean, base 10? Base 10 means we have 10 counting numbers that we use, 0 through 9, and all other numbers are made from them, from those digits 0 through 9. Now computers, we use binary numbers. Binary is base what? It's base 2. What does that mean? That means there's only 2 counting numbers or 2 numbers from which to choose, 0 and 1. Now, why do we use binary for computers? Is because computers ultimately only understand electrical signals, on and off, high and low electrical signals, which we traditionally represent as 1 in binary or 0 in binary, where 1 means on and 0 means off. So we have only those two digits, 0 and 1, which are known as bits. So how do we convert from binary to decimal? This is actually pretty easy to do. Each digit in binary can be either a 1 or a 0. Think of this, as I said, as on or off. And each of these digits has a value based on its placement within a particular binary number. And that value counts towards the total if its particular bit is set to 1. The least significant bit on the right, the least significant bit is on the right and its value is 1, and the values of each subsequent bit as we moved to the left increase by powers of 2, as you see here. I'm going through this quickly because I'd rather see an example. This is a lot of words. Words aren't helpful. Examples are more helpful. So here we have an example 8-bit numbers. This is an 8-bit number. Each one of these digits, look right here, 1110, 0100. That is an 8-bit number because there are 8 digits, and each of those digits we call a bit. A single 0 or 1 we call a bit. So this is an 8-bit number. This here is another 8-bit number. This here is another 8-bit number. The question is, what is the value of each of those 8-bit numbers in decimal, and how do we come up with that? How do we calculate that? So I say consider the following 8-bit number, which I wrote all right here, but I didn't specify the bit. I didn't specify, if you look where I'm pointing, this X. I didn't put a 0 or a 1 here. I did not put a 0 or a 1 here. For each of these, this is 8 bits. We have 1, 2, 3, 4, 5, 6, 7, 8. For none of those positions did I put a 0 or a 1. I put an X instead. But no, we could have put a 0 or a 1 in each one of those positions. And what I have underneath in this table is the value of each of those positions. And what do I mean by that? It's easiest to come back over to the tablet and to go back to something that we all know pretty well. But it's something that we probably haven't thought about in detail since, honestly, maybe 3rd grade. And what am I talking about? Let's take this number, 536. This is in decimal, so base 10. You could put here 10 afterwards. That means base 10. So this number 536, well, how do we get 536? Why is it not just 536? Like, how do we know it's 500 and then 30 and then 6? Well, we know that this is going back to what? 2nd grade. We know that this is the ones column. This is the tens column, right? And this is the hundreds column. So if I were to say, what is the value of each of these columns? For example, what is the value of this particular column right here? What's the value of that column? Well, the value is, I'm going to put another line here. The value right here is 500. Now, how did I get 500? Well, I have a 5 times, and this is the hundreds column. What does that equal? That equals 500. What's the value of this column right here? Well, I have a 3 times, and what's the value? This is the tens column. 3 times 10, what does that equal? That equals 30. And then what's the value of this right here? I have 6 times 1. This is the ones column, and that equals 6. So we add together 500 plus 30 plus 6, and we get 536. We all know how to do that, right? This is nothing new, but that's a good reminder because binary is the exact same concept here. I'm trying to grab my mouse. In binary, we do this exact same concept. So each one of these columns has a value. The value of this first column is 1. The value of this next column is 2. So in decimal, we say this is the ones column, this would have been the tens column, then the hundreds column, then the thousands column. Well, in binary, this is the ones column, this is the 2, this is 4, this is worth 8, this column is worth 16, this column is worth 32, 64, 128, 256, 512, 1024. It's going by powers of 2. That's the value at each column. Now, each of the x's above, as mentioned, could have been a 1 or a 0. So the value of that particular bit is going to be based on its position. And now let's give some examples. So here, look at this particular number, 1000, 1101. And I drew it out here, spaced out so we can look at each individual column. All we do is we add up the decimal values for each bit that is a 1. So for example, let's start on the left. We have a 1 right here. What is the value of this column? It's 128. So here, we take 128. Where's the next one? It's right here. What's the value? 8. So this, we're going to add an 8 to try to get the decimal number. Where's the next one? Right here. What is its value? A 4. Cool. We add 4. And finally, where's the very last one? Right here, and its value is 1. And so we add 1. So 128 plus 8 plus 4 plus 1. You take a calculator, you get 141. So we see that 1000, 1101 in binary is 141 in decimal. Let's do another one. Here, this number, 0110, 0010. We write that number down and we look at the values in each of the columns. And again, it's easy to generate these values. If I come back over to the tablet, let me erase what's here. If I wanted to just generate those values, the first value is a 1, the next one is a 2, and it just keeps doubles. 4, 8, 16, 32, 64, 128, right? That's how I generated that. And so now, if I just want to throw in a binary number, and I want to know what is the value of that number, what if I had right here 0, 1? I'm going to write down the one that we had. 0, 0, and we have another 0, and then 1, 0. So how do we get the decimal value of this particular binary number? We just go over, we identify any column that has a 1, right here, and right here, and we add the decimal values together. 64 plus 32 plus 2, and in fact, when we do that, we get 98. So 0110, 0010 in binary is 98 in decimal. So here's another example. How do we convert that one? And it's just showing you the exact same things that we just went over. So that number is again 64. This is 64 plus 32 plus 8 plus 1, and that will give you 105 in decimal. And we have 2 more examples for your viewing pleasure if you just want to practice this later and calculate that. So here's some other ones that are short ones and worth practicing, because this is what we want to be comfortable. If I give you this binary number and I say convert that to decimal, and now you're like, okay, wait, how do I do that? Well, the easy way is just remember, this right here has a value of 1, this has a value of 2, and then double. This has a value of 4, this has a value of 8. But we only count the values if the bit is on. So here, on meaning it's a 1. So this is 8 plus 1, and we get 9, and that is what we expected. Here, what do we have? Again, the first bit has a value of 1, then a value of 2, then a value of 4, and then a value of 8. Let me draw this one out. We have 1010. Let me erase this. So we have here 1010 base 2. That's binary. We want to know, what does that equal in base 10 in decimal? And the answer is it equals actually the number 10. Well, how did I get the number 10? Because look at the values of each of these columns. Remember, this has a value of 1, this has a value of 2, this has a value of 4, and keep doubling. This has a value of 8. So all we do is we look at all of the spots where all of the bits where the binary number is a 1. Well, that's a 1, and this is a 1. And now add the decimal values together, 8 plus 2, and we get 10 in decimal. So 1010 is 10 in decimal. What about 111? 0111. Well, this is going to be 1 plus 2 plus 4. That's 7 in decimal. What about 1111? 1 plus 2 plus 4 plus 8. That's going to be 15. And we got one more, and that's just going to be 8. So these are 4-bit numbers, right? Why do I say they're 4-bit numbers? Because there are 4 bits that make up each number. 1, 2, 3, 4 bits, right? We should be comfortable taking a 4-bit number and converting it to its decimal. And it's such a popular thing to do. There's an entire chart that you can just search for. I'm about to show you one because it's something that you shouldn't memorize. You should just be comfortable knowing that, okay, I know, in fact, that I have here these values. Let me erase this and this. Let me erase this. So whatever, if I said generate for me 13, give me the binary number that adds up to 13, you're like, okay, well, which of these numbers here add up to 13? Well, I need an 8. I need a 4. 8 plus 4 is 12. 12 plus 1, that's 13. Cool. So what binary number would that be? 1, 1, 0, 1. That's how you get 13. That equals 13 base 10 in decimal, 1101 in binary. So that conversion, once you've done it a few times, it's something that we should be a little bit comfortable with. And as a result, you're going to see there's even a table I'm going to show in just a couple of pages, which we can practice with and hopefully get us a bit more comfortable. So binary is easy once we understand it, but let's be honest, it's a pain to represent. To have all of those digits and to put all these zeros and ones, especially if you had a lot of them, it's a pain, which is precisely why we have hexadecimal. Hexadecimal is another numbering system. Hexadecimal is base 16. I want to think about that. Decimal is base 10. What are the counting digits? 0 to 9. Binary is base 2. What are the counting digits? 0 and 1. Even octal. Octal is another counting system. It's base 8. What are the counting digits? From 0 to 7. So if we have a base system that's more than 10, such as hexadecimal, base 16, what are those counting digits? Well, 0 to 15? Well, how do you even do that? That's kind of weird that there's 16 numbers, but you can't use 10 as a number, 11 as a number. The numbers are actually these. It's 0 through 9, which are the first 10 numbers, and then we have A, B, C, D, E, F. Those are numbers in the hex counting system, in hexadecimal. A, you could say, counts as 10, B is 11, C is 12, D is 13, E is 14, and F as 15. It's funky, but it's valuable, and we're going to see how valuable it is. So why hex? Because we want to easily be able to capture or to represent binary in a very succinct fashion. And hex allows us to do that beautifully. So if you look at this table, here are the decimal numbers from 0 to 15. Here are their binary equivalents, right? So we just did 13, which was 1101, right? 8 plus 4 plus 1 is 13. So here's their binary equivalents. And here are their respective hexadecimal values. So of course, 1 in decimal is 0001 in binary, and it's 1 in hexadecimal. Let's come to number 7. 7 in decimal is 0111 in binary, but it's just 7 in hexadecimal. So decimal and hexadecimal, from 0 to 9, they're the same. But now the decimal value 10 is the same as A in hexadecimal, all the way to 15. The decimal value of 15 is F in hexadecimal. Again, why is this valuable? Because it's very common to take a 4-bit sequence of numbers and to want to represent those 4 bits and to see those 4 bits. It's very common. Well, as you see in this table, we can take those 4 bits and we can very easily capture them with one hexadecimal value, right? 000, four zeros, 0000 goes to just 0 in hexadecimal, all the way up to 1111 goes to F. So these 4-bit binary numbers all very succinctly map into a hexadecimal number, which is why it's used, because ultimately it's easier if you wanted to write down 32 binary numbers, you could use just 8 hexadecimal digits to represent those 32 binary numbers, which makes it much easier. All right, maybe that was a bit painful, but hopefully not too bad. Why are we talking about this and why is it important? Again, computers understand only zeros and ones. That's it, on and off. So imagine if we had to code our programs with only zeros and ones and your code looked like this. Let me be very clear. If that was the case, I wouldn't be here. I would not have joined this industry, not in academia, not in industry. No one would want to code only zeros and ones. What a disaster, right? You wouldn't be here either. But we want to develop our languages, our programs in high-level languages like Python, like Java, like C#, C++. And thank goodness, as we know, we're not coding in ones and zeros. We're coding with these English-like commands. So what this means is, if the computer only understands zeros and ones, but we're typing in English, we're typing these commands on the keyboard in English, and the computer therefore has to have a way of mapping a single keyboard character into zeros and ones. Allow me to repeat that. Your computer only understands zeros and ones, but you're typing in print to print. Well, your computer does not understand the letter P. It doesn't know what P is, but it knows zeros and ones. So every single character that you type has a binary equivalent, and that is called an encoding. What is an encoding? Mapping a character to its binary representation is called an encoding. Now let's bring all of this together. One of the most famous and original encoding schemes is ASCII. It's called a 7-bit encoding scheme. What does that mean? It means that there are 7 bits that were used to represent a single character. So this character right here, the character W, is encoded with 1110111 in binary. Not only on my computer, on your computer, any computer across the world, 1110111 is the lowercase letter W. I'll give you one more. This is just one that I happen to remember. How about the lowercase letter A? Programming students normally remember A and capital A. Lowercase a has the value 97 in decimal, and capital A has the value 65. So what is lowercase a? It's 97 in decimal, but your computer doesn't understand 97, nor does it understand lowercase a. Your computer understands what? Binary. Well, how do we get 97 in binary? Well, just remember, we had the 1, 2, 4, 8, 16, 32, 64. That should be good enough. Which of these numbers, where do we need a 1 to add up to 97? Well, that I need 64. 64 plus 32 is what? That's going to be 96. And then one more over here is 97. So guess what? 0, 1, 1, 0, 0, 0, 0, 1. That is the binary number, and that is equal to the lowercase letter a. That's crazy. That's probably something you would never think you would learn in this, but that's important, and we're going to see why that's important. We want to understand these encoding schemes. So this is the ASCII encoding scheme. It allows you to take 7 bits, 7 unique bit patterns, and or take a unique 7-bit pattern and map it into a particular character on your keyboard. And this mapping is a universally understood mapping across the world. If you type the letter A on any keyboard in the world, you will absolutely get, it'll be translated to in binary 1100001. And every computer knows that is the letter A. Now, what's the problem with ASCII? Or what's the limitation? Because, well, here's ASCII. Before I get to the limitation, this is the ASCII table. So if you look over, where is lowercase a? Right here, it's 97. Z is 122. And each of these, of course, I'm not putting the binary representation because that would be a disaster. It'd be way too many zeros and ones on this table. So I'm only showing you the decimal values. And here are the hexadecimal equivalents with them, which you could very quickly map into binary. So, for example, we see that Z is 122 or 7A. And let me show you. I want to do one more of these. Let me show you why that's important. So we said that Z is 722. It's also 7A. So this is overkill, but it's going to take another minute, and it's worth looking at. Z is, again, 122. So Z, the letter Z, is 122 in decimal. And we saw that that's also equal to 7A in hexadecimal, base 16. So why is hexadecimal easy? Because to convert this number 122 into binary is a little bit, it's not challenging, but you have to do that whole process above, right? We had to go write this out, 1, 2, 4, 8, 16, 32, 64, next is 128. And you got to figure out which of these add up to 122. Well, I know it's going to be this and this is 96. I don't want to do this. Well, the 4 is going to bring me to 100. Right? 96 and 4 is 100 here. And I need to get 122, right? So if I add a 16, that's going to be 116. And now, oh, see, I shouldn't have even done the 4. It's just nasty. The point is you're trying to figure out how do we get to 122. Now I want to do it. 64 and 32 is 96. Here we have 106, 112. And here when I put on this one, this is going to be 120. Sorry, that should have been in red. That's 120, 122. If I did it right, I think that's what we have. If I did it right. Versus, check out this. What is just 7? Well, 7 is just 0, 1, 1, 1. That's 7. If you've done it enough, you already know that. And what is A? A is 10. What is 10? 1, 0, 1, 0. So now, if you look at that and you look at this, it's the same thing. We just need an extra 0 over here. Which was easier, to convert this number to binary or to convert the hex to binary? Because hex is always done in groups of 4. So the 7 is just 0, 1, 1, 1. That's a 7. The A is 1, 0, 1, 0. See how quick that was to go from hexadecimal to its binary. All right, that's enough talk on that. This is the ASCII table. Let me come back over here. This is the ASCII table. So ASCII was a big deal. It was super helpful. But what was its limitation? 128 characters is all we could map. With 7 bits, 2 raised to the 7th power. With 7 bits, if you make all possible bit patterns, you're only going to have 128 bit patterns. That's just not enough. That's not enough to represent. That's certainly not inclusive of much beyond lowercase English alphabet, uppercase, numbers, and some other keyboard characters. What about other languages across the globe? Clearly, ASCII was not enough. It was a great first encoding scheme, or one of the originals, but not sufficient. Unicode came to the rescue. Unicode was a 16-bit character encoding scheme. So how many characters, if you have a 16-bit pattern, how many different patterns can you make? Well, the answer is 2 raised to the 16. That will give you 65,000 plus different characters that you can map. In fact, encoding, Unicode has actually been extended to a 32-bit Unicode, which is over 1 million different characters. We're not going to look at that one. We're going to assume only 16-bit Unicode characters. So here, imagine you have this 16-bit sequence. Again, no one wants to type that out. That's too much. But in hex, that's really just BC 23. This is B, because B is 11, And here we have 8 plus 2 plus 1 is 11. C is 12. 8 plus 4, so we have B, C, and this is 2, and this is 3. So which is easier, these 16 bits or these 4 hex values? Of course, the 4 hex values are much easier to represent. So all of that is for what? Because if you needed to represent other values beyond what's on your keyboard, if you needed to print out other things beyond letters, digits, other characters, we need to understand that Unicode is this encoding scheme, and we're going to represent those 16-bit Unicode values with hexadecimal values. It's not something we're going to commonly be seeing or needing, but it's something we should be aware of. So in summary here, we have a binary number. 16 bits long is how we represent that in Unicode, because Unicode is a 16-bit sequence. We break that into its 4-bit sequences. So we take the first 4 bits here, the next 4 bits, the next 4 bits, and the next 4 bits. And then each one of those 4 bits can get broken up or can get converted into its hexadecimal equivalent. So this is 4, 1, 1, 0, 1 is 8, plus 4, plus 1 is 13, which is D. Again, we get 1, 1, 0, 1 is 13, which is D. And then, of course, this is just 0. All right, back to strings and characters. We're almost done here, actually. We have the OR and the char functions. These are 2 functions that are helpful that Python gives you to let you see what is the actual decimal value of a particular character. So, for example, if I were to type in, let me get rid of this stuff. If I were to type in the print, the ord of A, that will print for us 97, which is the decimal value of A. And then, of course, 97 in decimal has a binary equivalent that we've already seen, which was, what was it? It was 1, 1, 4 zeros, and then a 1. That was 64 plus 32 plus 1, right? That was 97. You could also take, how about this? We could say print the char value of, how about this, 99. Take a guess on what you think the char value, did I do that right? Yeah. What do you think the char value of 99 will be? And the answer is C. Because if A is 97, B would be 98, and the char value of 99, which again is represented in binary under the hood, right? It's really binary, and we're giving the decimal value, and the char value of that is actually C. So again, that's not something we're commonly going to need, but we should understand and be comfortable with the fact that all of these characters are represented in binary. No one wants to use binary, so we convert those binary numbers to either decimal, or in this case, or hexadecimal or decimal, so we can easily see the values of those particular characters. Escape sequences. How would you print a message with quotation marks in Python? What if you wanted to just print this? Print, he said, John's program is easy to read. Now we're trying to print a quote, right? When you quote someone, use quotation marks. What would happen if you printed this, right? If you came here and you typed in print, he said such and such. Well, but you want to quote the person, right? So you want to put he said, comma, such and such. What's going to happen? That's not going to work. Why? Well, because when you print, the interpreter sees that you have an open quotation marks. The interpreter says, I got you. I'm going to start printing a string. We print H, E, we print a space, we print S, A, I, D, comma, space. And then the interpreter sees, oh, you have a closed quotation? Cool. We're done printing the string, is what the interpreter assumes. Now you're thinking, no, we're not done printing the string. I got more stuff to print. But this closing quotation tells the interpreter, no, we're done printing the string. So how do you print a quotation mark? So instead of the quotation mark identifying the starting point or the ending point of your string, how do you actually print that quotation mark? And the answer is you have to use what is called an escape sequence. What you do is you put here a backslash, and you put one right here as well, before any quotation that you would like to see printed. So if you check that out, we actually printed the quotation by putting a backslash. What does that actually do? Well, once again, let's follow this one. Open quotation means to the interpreter, oh, I'm going to print for you a string. I got you. So the interpreter says, I'm going to print the H, the E, the space. I'm going to print the S, the A, the I, the D. The interpreter says, I'm going to print a comma for you. I'll print a space. And then the interpreter sees this backslash. And the interpreter says, whoa, you're doing a backslash? That's an important character. And what it tells the interpreter is the next character should be treated in a unique fashion. So when it sees this next quotation mark here, this double quotation mark, the interpreter is going to not close your string and instead it realizes, you must want to print a quotation. And that's precisely what it does for you. It prints a quotation mark. So what if I just wanted to print, it's weird, what if I wanted to print 3 quotation marks back to back to back? I would do this. That's funky, but this is the start of the string. And then we say here, print a special character, or do something special. What is that special thing? Oh, print a quotation mark. Do a special thing, do what? Print a quotation mark. Do another special thing, what? A quotation mark. And then finally here, that's the closing quotation mark of the string. Very funky, but that's how you would print quotation marks. That's not important, but it allows us to introduce escape characters. It turns out there's many escape characters. Some of these are very common. Arguably, the most common escape character is to do \n. This one's a big deal. So what if I wanted to print A, B, C, but I wanted to print each of those letters on a different line? You would normally have done what? You normally would have printed A, then printed B, and then printed C, right? Each one gets on its own line, and that was super big brain. I love that. I got to put that. That was a super big brain that I did not actually put here quotation marks. So we want to print A, B, and C, and we use quotation marks, done. What if we only want to do it on one line though? How would I print A, B, and C with one print statement, but each on a different line? I do this. A \n is an escape sequence, and what it does is it says print a new line. I can put an extra \n, and here I put an extra \n. Now we're printing 2 new lines between each one. So that is a very common escape sequence. You can also put a tab if you wanted to print a tab, \t. And if you noticed, it tabbed over this A. Those aren't spaces, that's a tab, right? So you can print a tab, you can print a new line, you can do other things. Printing without the new line. We've seen this, but it's worth covering very briefly. If I wanted to print here, hello, and then I want to print on the next line, world. Hello, world. Let's run that code. We get exactly as expected, hello on one line, world on the next line. But what if I don't actually want to end this line after printing? I want to keep the cursor on the same line. What I could do is this. I put a comma, and then I say end equals, and I put a pair of double quotation marks. And what that does is it keeps the cursor on the exact same line. It does not go to the next line and start printing world. Rather, world gets printed on that exact same line. Now, maybe a better way of explaining this is to put something inside this right here where my cursor is. If I said www, I put 5 W's. What is that really doing? It's telling the interpreter, end this thing that's being printed, end it with 5 W's. What if I did this? I said end it with 5 W's and a new line. Well, it ended it with 5 W's and then it put a new line. What if I said end it with 3 hyphens? Well, it puts 3 hyphens. or end it with 3 hyphens and a new line, it does exactly that, 3 hyphens and a new line. What if I say end it with just a new line? Well, that's the default. That's what would normally happen. If I did not put this at all, what normally happens is after you print the string, it puts a new line, right? So this is actually what happens under the hood. We're ending that print statement with a new line. So how do we not end it with a new line? We just erase that. When we erase that, we're telling the interpreter, print that line and don't put anything at the end, which means the next print statement will go on the very next line. We are almost done. This was examples of that one. We have a string function I wanted to show here briefly, how we can convert a number to a string. Not super exciting, but it just shows how given a number, if you put that number inside parentheses and use the string function, that number will then become a string and it will no longer be a number. That's helpful when you're concatenating with printing. Final thing to discuss here is just an introduction on objects and methods. What are objects and what is OOP? OOP stands for Object-Oriented Programming. And that's all we need to know for now, because we're not going to be talking about OOP and Object-Oriented Programming. But what's important is to understand that in Python, everything is an object. All numbers are object, all strings are objects. Everything in Python is stored inside an object. And this is different from many other languages. And you might be saying, well, what do you mean an object? What is an object? Consider this assignment, A equals 777. What's actually happening? You may have thought, I'll come back here to the tablet, you may have thought, if I say A equals 777, you may have thought here that, what does that mean under the hood? A equals. You may have thought that A is basically a variable, and here's the space in memory, and we're storing 777 inside that variable. That's not what's happening. What's actually happening, oops, that wasn't the tablet. Well, here we go, we're back at the tablet. What's actually happening is we're not, so again, you may have thought A is this number 777, and here is our space in memory. Let me do that again. A is, again, 777, and here's A, and you may have thought here's this space in memory, and we're storing 777 inside that space in memory. But that's not what's happening. What's actually happening is what you're going to see here, is that A is really storing an address. And what's inside that address, or what's inside A is an address that points over to the object in memory, and that object in memory has the value 777 inside of it. Let me show you this in Thani. So in Thani, previously we opened up just variables. I went to view variables. And let me type this, x equals, or let's do A equals 777, like the example we showed. Print A. So if we, of course, run this code, it'll print 777. Well, let's debug the code. When we debug the code, and I'm going to hit this icon to step into, so it sees this line number 2, and so we go to the right side of the assignment, it sees 777, and it saves 777 into the variable A. So here we show that A is 777. And we continue and we print it. We print A is 777, done. So now let's really show you what's happening. I'm going to come and click on View Heap. And this is going to get funky now. So check this out. When I debug it, what happens? We have an assignment. We go to the right of the assignment. This is really what's happening under the hood. Well, 777 is saved into this memory address, 2218C, this is a hexadecimal memory address, 7B6850. That's where, on your computer, that's the address of where the number 777 is saved. And what actually gets saved inside A is that address, if you look here. So what's saved inside A is a variable. What is saved inside A? It's the actual address of the object. Now, if we go to the object, what's inside that object? 777. So coming back here to the slide, this is really what's going on. If we say A is 777, an object is made with that number, and what is actually saved inside A is the address of that object. What's the takeaway? Why is that valuable? Because if you know that something is an object, then you know that there are operations that we can often perform on these objects. And these operations are called methods. So here we have S equals welcome. Well, this is a string object. This welcome string, it's actually an object. What's the value of knowing that? The value of knowing that is because it's a string object, there are operations, aka methods, that we can perform on that object. So if I have S equals welcome, I can do S dot lower. Check this out. Come here, S equals, let me type. It's not letting me type. Oh, I'm still debugging. There we go. S equals welcome. Let me print S. Then I'm going to print S dot lower. What if I print S dot upper? Those are operations, methods that I can perform on object S. Let me make some of this capital so we can see what it's doing. So here, if I just print S, it's the funky uppercase, lowercase combinations. But I can lowercase it or I can uppercase it using one of these methods. It's a string method, and we're able to have access to that string method because a string is an object. So Python also gives us this ID and this type functions, which tells us the type of an object. So here I can print what is the type of S, and I can print what is the ID of S. This is probably the only time you'll ever see that. I'm not even going to ask questions about this later, but just to show you, it's good for new programmers. The type of S is string, and what is the ID of S? It's this number. You're like, what the heck is that number? That's actually the address, but it's represented in decimal. So if you were curious and you wanted to pause the video, you could take this number, go to an online converter from decimal to hex, and this number will be the exact address here in hexadecimal. So the ID is the actual address of that object in memory, which is shown here as well in hexadecimal. You're never going to see those again. Literally remove that from your mind. Not as important. What is important is to know that these strings are objects and that there are methods. We saw the upper method, lower method. You have strip is a method. It removes white space, and it turns out there are so many other methods. And these are not things you memorize. These are things you look up. You just type in Python string methods, and you click on this first link and look at all of these methods. Converts the first character to uppercase, returns a string that is centered. Count returns the number of times a specified value occurs in a string. Let me click that, for example. I love apples. Apples are my favorite fruit. Text.count apple. Interesting. So you come over here and you're like, well, let me test that out. S equals, give us a string. This is now a long video. It really needs to finish. So how about I type in s.count, and we want to count the number of O's, or the number of letter O's in that video. We have one here, we have one here, we have one here. Was it 3 of them? No, it was 4. Where's the 4th one? It's somewhere in there. 1, 2, 3. Oh, the TO, 4. That's yet another method. This was method count. We have a count method. I don't memorize these things. There's all kinds of things. Is decimal. Is alpha if all characters are alphabetical characters. Is digit if all characters in the string are digits. These are all kinds of cool methods that are helpful to you when solving a particular problem. Like you could ask someone, enter their social security number or enter their phone number, and you could check if all of those are digits. S dot is digit, and it will print true or false. In this case, it's false because none of these are digits. But if you ask someone for a phone number here, and you put 555 1234, does that string contain only digits? In fact, it does, and it prints true. So to know that there's all these methods available to us is super helpful, and we're going to be using them as we're solving more programs as we continue on in the videos. That's it. It is a long video. Hope we're okay here. Reach out, ask questions, leave a comment. It's been fun. Take care, everyone.